Hey y'all, my name's Allie. I'm here to give you some helpful tips and tricks for Calc 1, starting with rates of change and discontinuity. So one of the things that is super important to understand, first of all, is the words rate of change and slope will be used interchangeably, right? So the rate of change refers to the rate at which the function value changes as the x value changes. So that's where this equation here comes in. You'll definitely recognize that from one of your algebra classes. It refers to the change in y over change in x, and generally that's used to find the slope of a straight line, right? So kind of jumping into applications of that equation, those go into a lot of the equations for lines that we end up having, right? So this first one is slope-intercept form, right? You have the slope here and the intercept here, right? That's the m is the slope, the b is the intercept. And the following one is point slope, right? So you have your slope still, and then you have a point, right? You're given some x and y coordinate that you use along with the slope to make an equation in the form of y equals something, right? So the first thing I want to do is jump into a couple examples. So obviously we have the first example is a straight line, right? The equation y equals x starts at the origin, and for every one point you go across, or you go to the right on the x-axis, you go up 1 point on the y-axis. So if I were to look at the slope of this line, right, the slope would simply be 1 because I have y here. Here's my y2, and that's at 2, 2. So my y2 minus y1 over x2 minus x1 is simply 2 minus 1 over 2 minus 1, which is just 1 over 1, which is 1. So my slope for that line right here, the one that we just looked at, y equals x, is simply 1. And you can also tell that because if you were to write this equation in y equals mx plus b form, your m would be 1 and your b would be 0, right? So there's a couple tips and tricks, little reminders from algebra. I know a lot of people might not take algebra and calculus back to back, so there's a couple reviews. A couple other things I wanted to go over is some special slope cases, right? So this first one here is for a horizontal line, and that's going to be something that's super crucial to what calculus means and why we use it, right? So if you remember, the slope of a horizontal line is always 0 every time, because if you think about the equation, your delta y, right, how it's changing vertically is 0, and your delta x would be, I don't know, 1, 2, like if this is my 1 and 2, I would have no y change over an x change, so it would be 0 over 1. So that's another kind of conceptual thing that becomes super, super critical when we start looking at some further concepts down the line in calculus. Always, always, always remember that the horizontal line has a slope of 0. Something similar, right, is the vertical line. It can't be 0 because we have plenty of y change and 0 x change. So if my delta y, if we're looking at, for example, 1 and 2, my delta y would be 1 and my delta x would be 0. So as of right now, this is undefined, right? Because you can't divide anything by 0 because anything times 0 would be 0. So as of right now, this form is undefined. If you were to approximate, instead of 0, if you were to approximate it as some really, really, really tiny number, like 0.000001, for example, you would get a massive magnitude, which is why sometimes a vertical line is considered to have a slope of infinity, because the smaller you make that step, and technically that horizontal step in the x direction is 0, because that step is so small, it becomes infinite. And that's something to remember generally in math. If you divide a number by 0, it's infinity. So we've gone over a couple pretty simple linear cases. We've gone over a normal line with some sort of angle. We've gone over the special cases of horizontal and vertical lines, but we oftentimes in mathematics know that not everything can be modeled by a straight line. And ultimately, that's what math is, right? We're trying to understand some system by fitting an equation to it. So what happens if example 4 is the case? What if I'm trying to model the slope or the rate of change between these 2 points, right? It gets a little bit goofy because it's nonlinear. So you can't use the y equals mx plus b trick we used up here because that doesn't fit that form of the equation. So we need a new way to define the rate of change for a nonlinear function. So how can we do that? So it can't be the slope because the slope of this function here is changing constantly, right? But what we can do is we can approximate it. So if I only care about the rate of change between these 2 points, what I can do is I can draw a line here connecting those 2 points, and that straight line that I draw will be my approximation, and I'll find the slope of that line. We call that a secant line, right? So a secant line by definition is a tool that we can use to approximate the rate of change of a function that's not linear, right? So for example, a quadratic function, which is what this is. And basically what we end up doing is we can say that if we have that linear approximation, we can find the approximate rate of change between those 2 points. And so as promised, my goal is to make all of this stuff super transparent for you, right? So a lot of these terms mean the same thing. So for example, up at the top, we talked about how rate of change and slope are the same thing, right? They're used interchangeably. Here, the slope of the secant line and the average rate of change are the same. And we'll go into that in a second, but that's super important to remember because that'll kind of make it a little bit clearer why we use the secant line versus what we'll talk about next, which is the tangent line. So real quick, jumping into what a secant line is, we'll look at this example first, right? So we have this curve, we have our y equals x squared that we were talking about before, and the green dots on that line represent the 2 points that we're using, like to approximate those rates of change throughout. And that dotted purple line connecting them is the actual secant line that we formed. So a lot of times questions pertaining to secant lines will either ask you for the slope of the line, the slope of the secant line, or the equation of the secant line. So let's first talk about the slope of the secant line. Another hint that I want to drop for you is that the phrase find the slope of the secant line and find the average rate of change between 2 x values are the same question. It's the same question, it means the same thing, it's the same process to find the solution, exactly the same. One other thing that it's super important to notice is that in these situations, for a secant line, they always give you 2 points. So for example, it would be between x equals 1 and x equals 2. Those are the 2 that we're using in this example, but it can be any 2 points on the line, or on the graph, I'm sorry. So how do we find a slope? That goes back to up here. This equation that you should know, pretty familiar with because of algebra. If you don't remember it, it goes back to that whole delta y equal over delta x, rate of change of a line, all of that. That's what that equation is. So we use this equation to find the slope of the secant line. We have our 2 points. So our first point would be x1, y1, and our second point would be x2, y2. It doesn't matter which x value is x1 and which is x2, right? So I could have called this x1 and the other one x2, right? But what I need to make sure is that this and this match. So if that is going to be x1, this has to be y1, right? So it doesn't matter the order that I assign them, but it matters that the x value and the corresponding y value match. So let's just go ahead and move forward with the example that I had drawn out, right? Where the coordinate closest to 0 is the first one and the coordinate further away is the second point. And then all you do is plug and chug, right? So the x coordinate of the first point is 1. That's where this one came. No. That's where this one came from. the x coordinate of the second point is 2, that's where this 2 came from. And similarly, y1 is 1, and y2 is 4. And then you just plug those into the equation, and you should get 3/2 as your final slope. So that would be the average rate of change of the function x squared between x equals 1 and x equals 2. That should also be the slope of this line that we used to approximate that rate of change between those 2 points. That's also the slope of the secant line. So again, m is the slope, and because we were given 2 points to use, that's the slope of the secant line. But further advanced equations, more advanced questions will ask you what the equation of the secant line is, because a lot of times we don't necessarily just need the slope to understand the behavior, we need the entire equation of the secant line to understand the behavior of the entire graph between those 2 points, right? Because I could draw that same slope right here, right? And that wouldn't necessarily define the equation that I'm trying to model. So I need the whole equation of the secant line, because that tells me that it is exactly where it is on that graph. So I've already found the slope. That's the good news. The slope here is the same as the slope up here. It's exactly the same. So I can just basically copy and paste this 3/2 right down to here, right? So those are the same value. You don't have to recalculate it. And the better news is that you've already basically got your x1 and y1 because you defined it up here to solve it anyway, right? So your x1 is this value here, and your y1 is the corresponding function value, right? So that's it right here. So basically it's just plug and chug again, right? So y minus y1, so y1 is this 1 right here, and x1 is this 1 right here. So basically in this equation, or in this model, our point was 1, 1. That won't always be the case. It could be 2, 3, it could be 10, 4, it can be whatever. But it's basically just plug and chug. And then from there, you distribute the 3/2 into both the x and the 1. And then you simplify, because all equations, especially on those virtual homework websites, will ask you to submit basically just this half. It'll already have the y equals part typed out. So always simplify it to y equals something. So we're going to move on to another example, right? And look at this goofy looking, crazy graph that you'll probably end up seeing more things like this in the real world. For people who are going into engineering, a lot of the graphs look kind of goofy like this. But here's an example of my secant line, right? So I have my 2 points, my green dots are my 2 points, and I just draw a straight line connecting them. So that purple dotted line is my secant line. What is wrong with the way that that secant line is allowing me to approximate the rate of change between those 2 points, right? So that does reflect, by definition, the average rate of change, right? And you can kind of conceptualize that because this starts decreasing and then it goes up and then it comes right back down, so that you can kind of conceptualize that does reflect the average, because you've got some negative and then you got a lot of positive and then you got some more negative. So it does represent the average, but what does that actually help me understand about this function, right? Because that's basically telling me that for all intents and purposes, we could just connect these 2 dots, which in a lot of the cases that you would use calculus for, especially in engineering, that's not necessarily true, because you might need to know a lot about what the nuances in this behavior are. And you can't do that if you approximate it as a horizontal line or like a straight line like it is right now. So a lot of times what happens is, in more complex cases, secant lines are less and less reliable. For example, if I drew another one from here to here, I'm missing all of this funky behavior that happens down here, and I'm missing the peaks up here and here. So a lot of times secant lines are an over approximation. So how do we compensate for that? That's where the tangent line comes in. So as a reminder, the secant line was connecting 2 points to approximate the rate of change of a nonlinear function. The tangent line is very, very similar, except you're using 1 point, not 2, which means that your line it won't cross the graph at all. it'll kind of like brush up against it, and it'll only touch the graph at one point. And that allows us to make a super approximate, a super accurate approximation of the rate of change. And just as the secant line and the average rate of change are interchangeable terms, so is the instantaneous rate of change and the tangent line. So going into an example, this is kind of what I mean about it brushes right up against it, right? So here's the point I'm approximating, and you can kind of just imagine sliding that tangent line up against it as if you were trying to only barely touch it. So that's what it looks like visually. But what you'll notice is that the actual process of finding the slope and equation are very similar. There's just one slight issue, right? So before, remember, I was given 2 points. I was given this one and this one. So that was my x1 and my x2, and then the corresponding y1 and y2. What happens when I'm only given the 1 point, right? So I was only given this point right here, because remember, it only crosses at that 1 point. So the question would be worded something along the lines of, find the instantaneous rate of change at x equals 1, right? So I only have x equals 1 to go off of, but I know for my slope equation, this equation here, I need 2 points. So what can I do? I know that it's supposed to only touch at 1 point, but because I need 2, I need to come up with a second point somehow. So what do you do if you're trying to average two numbers that are very, very far away from each other? It comes up as something that's pretty much halfway between them. The same principle happens if you're trying to average two numbers that are right next to each other, like very, very close to each other. So for example, x equals 1 and x equals 1.01, right? Those numbers are super, super close. So when they average out, it's going to be 1.005, which is incredibly close to the original 1 that we were trying to look at. So basically what we're going to do is that's exactly the principle that we're going to piggyback off of, right? So because we need that second point, and because we want it to theoretically be just the 1 point, we're going to pick a second value, a second x value, and we're going to plug that in to the function and get a second y value. But this x that we pick is going to be very, very, very close to the original x value. So to get a perfect, to get a near perfect approximation, you would want to pick something like 1.00000000 forever and then 1, right? Because that's the closest you could possibly get to x. For a realistic, like I'm taking a quiz and I need to plug all this into my calculator, you want to pick something close, but something that you'll be able to distinguish, right? So I'm given 1, I'll pick 0.99, or I'll pick 1.01. Doesn't matter which side of x you fall on. I tend to always do a little bit higher than the number I'm given, but that's totally up to you. Basically, the premise is you follow the same steps. I have my m equation. I have 2 points now that I plug into. I have my 1 for my x1. I have my 1.01 for my x2. And then I've plugged in this 1 into this function. And I got this. Obviously, 1 squared is still 1. And then I plugged in 1.01 into that function, and I got 1.0201. And I did not do the math on that, what that simplifies to, but it gets some number, right? And it'll get some number very, very close to this original 3/2 that we got. But it'll inherently be more accurate because it's a smaller window. Now, what if the question was to say, find the equation of the tangent line? It's the exact same process. So I take the slope that I calculated above, and that's what goes in here. And then I take my x1 and y1, and I plug them in. And then I solve for y. So the processes themselves are super, super similar, but inherently the tangent line is more accurate. So here's just a little figure that I use to demonstrate this, right? So if I were looking at this point specifically, right here, that purple dotted line, or the the pink dotted line would be the tangent line for it. But if I was looking at this point over here, the yellow one would be the tangent line. That would be the tangent line for the blue. The green is for that dot. The purple is for this one. And the red is for that one. So you can draw a bunch of you could draw an infinite number of tangent lines across any curve. Whereas a secant line, you're much more restricted because it has to go across 2 points, right? So that's the benefit of a tangent line, is you can look at any single point at all. So if I need to draw tangent lines like this across any point of the curve, what happens if I don't really know what the graph is doing at a certain point? That's where discontinuity comes in, because for example, in a piecewise function, which is what this is, I don't know if you guys remember that from algebra or pre-calc, but a piecewise function basically says that for the x values between this range, this is the function. So that describes this. And then for the x values between this range, this is my function. So that's where this diagonal line coming down comes from. And because none of these are inclusive, so none of them are like less than or equal to, or like greater than or equal to, this is an unfilled dot. So essentially there is no value of the function at x equals 2. So that's one of the things that you should definitely notice about this graph. There is no value of the function at x equals 2. But even if there was, so let's just spitball for a second. And let's just say this was less than or equal to, and I'm going to fill that in. Let's compare those situations. So I've drawn out my tangent lines on a simple parabola. So not pointy, it's just gradual, slope up, curve down, slope down. You can see exactly how those tangent lines progress, right? So it goes slope up, slightly slow down the slope, definitely slow down the slope. Okay, now I'm a negative slope, and now I'm a really negative slope. So that's the progression of a parabola, right? You can't necessarily follow that same progression on this curve, right? The curve on the right, because I have my slope up, except I have the same slope up, and then suddenly it switches to down, but I don't really know, like, is this supposed to be flat across? Is this supposed to be like some gradual change? Because it spins on a dime, because it rotates immediately, pivots across that point, you don't know what that actual slope is going to be. So you don't have an accurate way to draw the tangent line at this peak here. So that's where discontinuity comes in. And there's 3 primary types of discontinuity, right? The first one that we dealt with up here before we filled it in, when it looked like an open circle like this, that's called a point discontinuity. Because if I were to just plug in an x value at that point, that would fix the discontinuity. It would now be continuous. So that's that. So it's a hole in the graph. An infinite discontinuity is some kind of like complex behavior where it involves going to positive infinity or negative infinity at some asymptote. So because it goes to positive or negative infinity, that kind of gets complicated, because how would I draw a tangent line to reflect what's happening at x equals 0, right? Because sometimes it goes up, sometimes it goes down. I don't know. So that's what an infinite discontinuity is. The last one is called a jump discontinuity. So you'll have, especially in a situation with piecewise functions, you'll have something that looks like this, where if x is less than x1, it'll be, for example, y equals 2. And it'll go all the way until x1. And then it'll say something about like if x1, or if x is greater than x1, it's 1, right? The value of the function is 1. But I have this really strange, I don't know what's going on in this region. How do I draw a tangent line between those 2 curves? How do I draw a single straight line that tells me how I got from this point to this point? I can't. So that's called a jump discontinuity. So there's a couple things that these have in common, right? So if I look at the point discontinuity and the jump discontinuity, right? Both of those could be written by piecewise functions, right? That's the first thing. So what you're going to do is every time you're dealing with a rate of change or a slope or a secant or tangent line problem that has piecewise functions, what you're going to do is you're going to want to check your connection points. So for example, in this function here, your connection point was 2. And if you look at our graph, before we filled this hole in, that was our issue, right? Our issue was exactly at x equals 2. So a lot of the times that's what's going to be your giveaway, right? So if you have a piecewise function, always check the value that they have in common between the two chunks. And if there's a third chunk, so for example, say if it was x squared for 4 is less than or equal to x is less than 10, for example, also check 4 because 4 is now a connection point too. So always check your connection points for piecewise functions because you'll either sometimes have a jump discontinuity or a hole in the graph. Now, if you were to compare the infinite discontinuity and the jump discontinuity, the commonality is that for a single x value, the y is approaching 2 values depending on how you look at it, right? So if I'm walking down here, down the negative x-axis towards 0, and I'm trying to understand what the function is doing, from here, it's going way down to negative infinity. But if I'm going to approach x equals 0 from the positive x-axis, from here, it looks like the function goes to positive infinity. If I were to do the same, if I were to follow the same logic, I'm approaching x1 from the left, it looks like it's approaching 2, right? Because this value is 2. But if I'm approaching x1 from the right, it's approaching 1. So the commonality between infinite discontinuities and jump discontinuities is that it's a lot of times you'll have a situation where an x value and an x value is approaching 2 different y values depending on the situation you look at it. And that is an excellent segue to the next video, which is about limits, because that approaching the logic of I'm going to approach this value by essentially walking down the function is what a limit is. So this is the end of video 1. Go ahead and, if you're interested, watch video 2. It's about limits and understanding them numerically and graphically. If you enjoyed the video, please like and subscribe and let me know in the comments if you have any other questions about it. I'd love to know, and I can make a follow-up video if that's relevant. Have a good one.